In this video, we're going over the background for Lab 13, which is titled Synthesis of Soap. The experimental goals for this lab are: students will learn the process of synthesis of soap, students will understand the cleaning action of soap, and students will explore the cleaning capacity of soap with hard water and soft water. First, let's define what is a soap. Soap is a molecule that is obtained from the base hydrolysis reaction of fats or oils. This reaction has basis in organic chemistry. It is known that when the functional group ester, and we can see it here on reaction 1, reacts with a strong base like sodium hydroxide, and the reaction is heated, there are two products that will be formed. The first one is a carboxylate salt, and the other one is an alcohol. In essence, when we look at our functional group, there's going to be a separation between the carbonyl portion of the ester and the single bond oxygen and whatever substituent is on that side of the molecule. If we apply that into fats and oils, as we can see in reaction 2, here we have palmitin, and palmitin is going to be the triglyceride of palmitic acid. So this triglyceride from palmitic acid, which is basically palm oil, when it reacts with 3 moles of sodium hydroxide and we heat them, we're going to form the carboxylate salt that we observed above. And that is specifically what the soap is. The alcohol in this reaction is going to be the glycerol molecule. Because remember that as we discussed previously, when it comes to triacylglycerols or triglycerides, which is the other word that we utilize, they are composed of glycerol and fatty acids coming together to make those ester bonds. So when we break them apart, then we have that carboxylate salt and that glycerol molecule. Now, if we look specifically at one molecule of soap, then understand that the area where we have the carbon double bonded to oxygen and single bonded to oxygen negative, that is known as the polar heads, because the carbon oxygen bonds are polar bonds. Then the area of the molecule that has just the hydrocarbon chain is known as the non-polar tail. This is important to note because one of the things that we know is that soap is going to interact with water. And since water is a polar molecule, then utilizing the terms hydrophilic and hydrophobic, we can define which area of this soap is going to interact with water. So that being said, the polar head is going to be the hydrophilic area of our molecule, meaning that it's going to be able to interact with water because it has the same polarity of water. On the other hand, the nonpolar tail is going to be the hydrophobic area of our molecule, because since it's not polar and it doesn't share the polarity with water, it's going to be afraid of it. So these concepts of hydrophilic and hydrophobic areas are really important when we're trying to understand how a soap actually does the cleaning action. As you can see in this figure, there are several steps for a soap to actually perform its cleaning action. First, the soap is going to be able to dissolve in water. And in this lab, you will be observing the difference of dissolving it in soft water versus hard water. But in general, if you have water and it's a soft water, overall, if you have a surface that now is dirty, and we can see in this image how this surface has been dirty by putting grease on it. Overall, what happens is that your soap, in other words, the surfactant, that molecule that is going to be interacting with the surface, the tails of your soap are going to orient themselves in order for interacting with the grease, because the grease is going to be a nonpolar molecule, and then the water, because it's the solvent, is going to be interacting with the polar head. Understand that agitation is the process by which we start beginning to separate that grease, that stain that we have on the surface, from the surface itself. And you can see that as the process continues, more soap molecules are going to interact with the grease, and then they're going to make these structures that are called micelles. These micelles, as you can see, in the middle is where we see the grease, where they are interacting with the tails of your soap. And in the outside of those micelles, we have the polar heads that are soluble in water. And that's how we are going to remove that stain, that grease, that molecule that specifically was used to soil the surface. Okay? Now, in the last part of this lab, we are going to see how are there differences when we have hard water versus when we have soft water. Let's define the difference between these two types of water. On the left side, we can see the description for hard water. Hard water is water that has high mineral content. In general, we understand that hard water is going to contain divalent cations. Divalent cations are going to be cations from group 2 in the periodic table. For example, magnesium and calcium. Often, when it comes to hard water, it has a characteristic taste, but it's a little bit hard to describe. Understand that hard water is formed when water flows through limestone and chalk. And it is important to note that if soap is actually placed in hard water, in the hard water, you can see in the image in the left that the soap has less effect at cleaning because of the presence of those divalent cations. A film or soap scum is going to form. So that's not going to allow the soap to have any action if you try to use soap that is already in hard water at cleaning a surface. On the other hand, we also have soft water. When it comes to soft water, and note that in this lab, the soft water sample is going to be distilled water. So necessarily there's not specific sodium cations in it, but just assume that they are in the sample. Soft water is when you're having a water that has less mineral content. Typically, it has sodium ions. And remember that sodium is one of those elements in group 1A in the periodic table. Soft water, on the other hand, it tastes a little bit salty. Now, how we make soft water is by actually passing the hard water through an instrument that is called an ion exchange resin, in which the divalent cations are going to be retained in the instrument, and then as is passing through, the sodium cations are going to be incorporated in the water. That's why it's called an exchange. You're going to exchange the +2 cations for the +1 cation as your water passes through the resin. And understand that soft water, specifically when we put soap in it, the soap has a good effect and we see a lot of foam. And you will see how the cleaning ability in a soft water sample that has soap is much better than the one compared to hard water. Overall, in this experiment, there are 3 parts that the students need to perform. Part A is an OLAPS in which you are going to observe the process of saponification, which is how soap it is synthesized. On part B, you will be watching a YouTube video that explains how a soap actually works in the cleaning action of a soap. In part C, you're going to be testing the cleaning capacity of soap by comparing soft water, hard water, and very hard water to each other. And that is an OLAPS. Remember that there are questions in the lab sheet that need to be answered for part A and part B. And on part C, you will be taking measurements of your soap solutions and the foam that it forms.